general relativity, step by step. I've got my expression for my stress energy tensor here, or at least 3 terms of it, for a perfect fluid. So in its rest frame, we've got as a matrix 0, 0, P. So what I'm going to do now is I'm going to remind myself that the stress energy tensor T alpha beta is actually a second order tensor. So what I'm going to do is to write down its write down its components in a barred coordinate system using the dix, 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 dix rules. So I'm just going to do that, and I'm going to use different colours just to make it a bit more fun. Okay, so T bar something something equals dix, dix. See, I'm writing the skeleton out again, as we always do. T something something. Right. So what I'm going to do is I'm going to use a red colour here for that first one there. That's unbarred and that's on the top, so that's got to sum with something on the bottom. Unbarred, unbarred. I'm going to change to green. That's a beta and that's a beta. And this is, of course, if I go back to black, I can write this out a bit more explicitly. That is summed over alpha and beta by the Einstein summation convention. Now I'm going to go to blue to do these terms here. I don't want to use alpha, beta, gamma and delta because that gamma there gets confused with this gamma here and it drives you nuts. So I'm going to talk about mu, and I've run out of colours, I'm going to have to use blue again. That's mu and nu. Going back to black, this is the barred system here, so that equals that bar, that bar. Now I'm going to write down, I'm going to write this out in a little bit of an odd way. I'm going to remind myself that I'm carrying out Lorentz transforms here. So if I just look at this term here, well, let's do them both. That is, it's the Lorentz transform. So it's just gamma, gamma, u, and gamma, and that's the 0, 1 and the 0, 1 term. So that's the time column, space, time, row, space, row there. And this one's the same thing as well, because it's the same thing, except it's got different indices. So the tensor I want to take is this is the stress energy tensor in its rest frame. So straight away I know that the only terms I've got to worry about are the terms where alpha equals beta, equals 0 for this one and 1 for this one. If alpha is not equal to beta, we're on the off diagonal terms of this object here, and so we can just ignore it. So we need these, we can just ignore those, which makes my algebra a lot easier. Let me just show you. Okay, well, let's just do this. Let me just note what this term actually means. That's gamma if mu equals alpha. If mu equals alpha, we're on the diagonal, whatever it is, whether it's 0 or 1, we come out with a gamma. If we're on the off diagonal elements, that means that mu is not equal to alpha, and it's gamma u if mu is not equal to alpha. And of course this is the same, but we've got different named coordinate system, named indices here. So this one, this matrix here, or this entry here, is going to be gamma if nu equals beta, because the top matches the bottom, and gamma nu if nu is not equal to beta. Looking at that equation there, it's a bit intimidating to see all these different colours and the summation and these curly differentials and the bars and all this rubbish. But what you've got to do with any tensor equation is just to simplify it. And if you can't grok the whole thing, if you don't understand the whole thing, well, what can you do? And you can always do a little tiny bit of it. Let's try evaluating t bar 0, 0 equals sigma over alpha and beta. I'm just going to write it out as a mu and an alpha, mu and beta. This notation here is almost universally used for that matrix there, where gamma equals the Lorentz transform. I think I've mentioned that, but a long time ago. Times t, and we're summing over alpha and beta, of course. So the only things we need to use are alpha equals beta equals 0 and alpha equals beta equals 1, because if alpha is not equal to beta, we move off the diagonal of this term here, and we can just ignore it. Equals 0, 0, 0, 0, t 0, 0. Let me just write it out and then I'll show you where it all comes from. 0, 1, 0, 1, t 0, 0. This term here is the alpha equals beta equals 0 term. This one is the alpha equals beta equals 1 term, and we're adding them because it's the summation convention. We're evaluating t bar 0, 0, so that tells me that mu, that's mu, equals 0. This one here is nu equals 0, which is why I've written down nu 0 here and here, and here and here. T 0, 0 plus... No, that's not right, is it? That should be 1 and 1. Because that one matches this one, and that one matches that one, because that's an alpha, and that's an alpha, and that's a beta, and that's a beta. Easy to get this kind of thing wrong. I've been doing this for a long time, and I still get it wrong. For this kind of thing, anyway. Equals gamma squared t 0, 0, because the indices match, plus, and then the indices don't match, so it's gamma squared. Actually, let's write it out in full. Gamma u, and then t11, which equals gamma squared rho plus gamma squared u squared p. There we go. We can factorize it if we want. Gamma squared rho plus pu squared. There we go, and that's equal to t bar 0, 0. Okay, so we've got this nice expression for the stress energy tensor, or at least the 0, 0 component of it, from the perspective of somebody who's moving with respect to the fluid. And I'm going to stop there. Stop.